All right, in this video, we're going to take a look at an important idea, starting with this note. We should note that not every single approximating polynomial needs to be approximating the curve or kind of starting from the initial point of contact that we saw up here, which was always when x was 0. There's no reason that I had to build my original tangent line there. I could have built a tangent line out at 1 and started having everything connecting at that value, or maybe at 2 or at 17 or at pi. It could exist anywhere. So we'll consider approximating a curve at an arbitrary value of x that we will call x0. When we do this, we're going to arrive at a new definition that accounts for the fact that we're going to shift where our starting point might be located. Here's what we have. If f can be differentiated n times at a value of x naught, so that's just some value out there, then we define the nth Taylor polynomial for f about x0. This is a very long title. An nth Taylor polynomial for the function f about or centered around x0. We define that to be the following. Okay, so essentially what we're going to be trying to do here is create another polynomial that we could use. And what we would like this polynomial to do is to still model difficult curves, but not connecting from 0, but maybe from some other point. Essentially, we're going to be trying to think about picking up our polynomials and shifting them. Really quickly, I'm going to just highlight something that hopefully you've seen several times in the past. You don't have to draw these pictures down, but I'll put them here. Let's suppose that I had a quadratic, a simple one, that was like y equals x squared. If I wanted to pick up that quadratic and shift it over, so maybe it started over here at 2, do you remember how I could actually write down a formula that would give me that appropriate shift? Well, you might be thinking that I could do something like an x minus a 2 squared. And that's exactly right. That by putting that kind of subtraction of where I want to be centered at, that allows me to shift everything over to that value. And what we'll see then is that's exactly what's going to happen when we write out our polynomial in the definition below. Here's going to be the definition of what we have. Instead of evaluating all of my different functions of f at 0 like we used to, we'll evaluate them at our new starting point. And every time, instead of writing just an x, we're going to have to write our x being shifted over, kind of like what we did with the parabolas up above. So notice that I'm going to get these same kind of crazy looking formulas with a bunch of different derivatives, dividing by factorials, and I'm still going to have x's raised to powers along the way, but they're going to be shifted. And so as I continue on here, I'm going to finally end with something like an nth derivative with an x0 plugged in over an n factorial x minus x naught to the power of n. And of course, if I wanted to, I could even write this all in a squished down series notation, which would look like, in this case, it would look something like this. I'd have a kth derivative with an x0 over a k factorial, x minus an x naught to the k. All right, so that way, again, k represents the power that I'm working with. And oops, I'm sorry, I'm not going to go up to infinity. I'm going to stop once I hit n, not going to infinity here. Okay, so this is what we call a Taylor polynomial. Remember that the last polynomials that were centered at 0, we called Maclaurin polynomials. There's no difference really between these, except that one starts at 0, that's Maclaurin, and Taylor can start anywhere in the universe that we want. So when you hear Maclaurin polynomial, you have to immediately think starting from 0. And when you hear Taylor, you have to start searching for where do you want me to start. If you take a look here at the next page, you'll see that I'm going to ask us to do this in a particular example. I'm going to say, can we find the first 4 Taylor polynomials for the natural log of x about x equals 2. And you can see here in the picture that at x equals 2, that's my starting point. That's where everything's connected. Okay, so let's take a look at how we would do this using kind of the definition that we had up above. The first thing that I might note is that my function here is the natural log function. And if I want to start going ahead and creating all of my different terms in my polynomials, I need to know derivatives of this function and be able to plug in the special x that I'm starting at, which is 2. So notice here that my 2 right now, that's my x0. Okay, so I'm going to start by just taking a look here at my function and its derivatives. All right, so I'll say we see that f of x is equal to the natural log of x. F prime of x is 1 over x. F double prime is negative 1 over x squared. And f triple prime is going to be 2 over x to the third. Notice if I want my first 4 polynomials, this is as far as I'm going to need to go, but I also want to figure out what happens then when I plug 2 into each of these values, or each of these functions. So f of 2 creates natural log of 2. F prime of 2 creates a half. F double prime of 2 creates negative a quarter. And f triple prime of 2 creates, what is that, 2 over 8, which is just a quarter. So if I want to start building my polynomials, it's really easy. Remember, my first polynomial will be P0. It's going to be the horizontal line that's in the picture up here. It's the boring one. This is just going to have only C0 in it. And again, keep in mind how we build those constants. For any constant, we take the derivative that we're on, we're going to plug in our x0, and then we're going to divide by n factorial. So here, when I do C0, I'm going to say take no derivatives, plug in the special number 2, and divide by 0 factorial. So in this case, I'm going to get natural log of 2 over 0 factorial, which is 1. When I do my P number 1, again, it's going to have the same starting term, and then it's going to have one more term that's going to be in front of my x to the first power. I'm going to find my C1 though. So for C1, I need to take my first derivative, plug in 2. I know that gets me a half. And then I'm going to divide that by 1 factorial. And then I'm going to write that as x minus 2, and that's going to be raised to first power. Notice again, I had to do the minus 2 because I was shifting over. If I was to go ahead and move on to the next term, or the next polynomial, I could say this is P number 2. This is natural log of 2. Notice here I could simplify this to 1/2 times x minus 2. And now I need to find C number 2. So that's going to say take the second derivative, plug in my special number 2. That gets me negative a quarter. And I want to divide that negative a quarter by 2 factorial. And then I'm going to do x minus 2 squared. Of course, I could clean that up a little bit, and I'll do that here in P number 3, where I'm going to get natural log of 2 plus a half x minus 2. Looks like I'm going to get minus an eighth x minus 2 squared. And then I'm going to try to find C3. That's again going to be 1/4 over 3 factorial x minus 2 to the third, which when I write all of this out as clean as possible, ends up looking like the following. So these would be some of the different polynomials that I could use to model the natural log function around the starting value of 2. This is a really powerful thing to be able to do. Okay. If, of course, you got questions on this, I'm going to encourage you to try to go ahead and start to practice this idea a bit more. And we'll look at least 2 more examples here in this section of how we can imagine starting to use this when we try to even write things like an nth Taylor polynomial, one that's a mystery length that we could determine later.